All right, so now that we know how to find a second derivative, well, what use is it? How do we make use of it? And it helps us to determine the nature of stationary points, but it also helps us to find points of inflection. Now, up until this point in time, we've certainly found stationary points of inflection. So we think of our quartic graphs and our cubic graphs. We also have just normal points of inflection, which we'll talk about a little bit soon. So, to find our points of inflection, what we're interested in, if we've got a first derivative dy dx, obviously gives information about the gradient. Where the derivative is equal to 0, obviously there are stationary points. Obviously, could be a maximum, could be a minimum, could be a stationary point of inflection. Yeah. So, if the second derivative is equal to 0, hang on. So, the second derivative equaling 0 gives points of inflection. All right. Now, they can be a stationary point of inflection or an ordinary point of inflection. Now, an ordinary point of inflection, if I consider just a cubic graph. So there's my cubic graph there. So as it starts to come back down again, at some point in time, if we think about the nature of it, the gradient here, I'll go back to purple, is 0. It's getting steeper and steeper and steeper until some point in time it starts to get shallower and shallower and shallower and comes back to 0 again. That point of maximum steepness, that's my point of inflection. Okay, so my graph is at 0, 0 gradient, steep gradient, and then it starts to make its way back down to a 0 gradient again. Okay? So that's what a point of inflection is. A stationary point of inflection. So if you think about the gradients, negative gradient all the way through there, a stationary point of inflection has, I guess I could have a negative gradient all the way through if I want to be consistent. Still negative, but the stationary point comes to a 0 gradient and then continues to be negative. So the difference being there, the stationary point of inflection will have a 0 gradient somewhere. All right. So where the second derivative equals 0 is where the gradient is at its maximum or minimum steepness. Okay. Right. Where f dash of x is equal to f dash of x is equal to 0. So where those two conditions occur, the first derivative and second derivative are both 0. There is a stationary point of inflection. All right. Because the gradient equals 0 at this point, this is also a maximum or minimum point of gradient, isn't it? So typically minimum. Oh, it depends, I guess. We've got a steep gradient into a 0 gradient into a steep gradient. So there was a minimum gradient there, wasn't it? Whereas if we're going the other way, it's a negative gradient into a 0 gradient into a negative gradient. So that makes that a maximum gradient, doesn't it? All right, let's have a look at our question here. So we've got our f of x equal to 1/3 of 4x cubed minus x to the 4. Okay, first things first. Actually, I should put that in red, be consistent with what I'm doing. If I want to find the derivative, I get 1/3 of 12x squared minus 4x cubed, which is the same as then 4/3 of x squared times 3 minus x. So straight away, we can see that at x equal to 3, I have a stationary point. All right. If I work out f double dashed of x, differentiate the first derivative, I get 1/3 of 24 minus 12x squared, which is 4x times 2 minus x, which means the second derivative is equal to 0 at x equal to 0 or x equal to 2. So I've got points of inflection there. So let's have a look at the little summary there. So at x equal to 0 and x equal to 3, from the first derivative, f dash of x is 0, so I have stationary points. So first use of my second derivative, at x equal to 0, hang on, so we'll go here first. At x equal to 3, the second derivative, f double dash of 3 is less than 0. So it's negative, which means it's concave down. And we haven't really spoken about that just yet, but we will. So if my second derivative is negative at the stationary point, it makes it a maximum. All right, so x equal to 3 is a max. If we come back to our second derivative, the second derivative is equal to 0 at x equal to 0. So as I said there, we have stationary points at x equal to 0. And because the first derivative is equal to 0 there also, it's a point of inflection. So I do know that at x equal to 0, I've got a point of inflection. And I do know that at, what we say, at x equal to 3, I have a stationary point that's a maximum. So I call that 0, 2, 4. So at x equal to 3, if I substitute x equal to 3 here anywhere, I haven't, that's disappointing. So at x equal to 3, what's the function equal to? 4 times 3 cubed, which is 81. Minus, so hang on, 4 times 3 cubed is not, that's 108. Minus 81 is 28 on 3, so it's about 7. So at x equal to 3, 27, maybe up there we have a maximum. And then what was my x-intercepts? We're at, so I factorise it, at 0 and 4 in red down there. So it's kind of like that. So the significance of 2, so there's my point of inflection at x equal to 0. At x equal to 2 for the purple function, I've got the graph increasing, 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 and then at x equal to 2, it starts to decrease. Yeah? So if I've got this sorted out correctly, hang on, of course I haven't. This isn't going to work, is it? There we go. There's our graph. I knew it was here somewhere. So the red graph is the original. Let's have a look at the sort of key points now. So my maximum, I'll pick a different colour. Pen, yellow. I've got my maximum up here at x equal to 3. I've got my intercept at 4, point of inflection at 0. Okay, now here, the green function there, let's take it a step at a time. So there's my derivative in green, okay, where the derivative is 0 corresponds to a stationary point. Probably should work with the colours. Derivative is 0, matches off to a stationary point. Where my second derivative is 0 corresponds to my point of inflection, okay, which also corresponds to there. All right, so by looking at the graphs, we now know that the second derivative is 0 at x equal to 2, so that's a point of inflection, x equal to 0 and x equal to 2. Because the first derivative is also equal to 0 at x equal to 0, that makes it a stationary point of inflection. The first derivative is equal to 0 at x equal to 3, which makes it a stationary point. Because at x equal to 3, my second derivative down here is less than 0, okay, that makes it a maximum stationary point. All right, so hopefully, like, it's a graph that we're familiar with, but just tying in the significance of the first and second derivatives, and when they're equal to 0, what's the significance of that in each of the functions. All right, we'll do a couple more. All right, so let's concentrate on our curve here. We've got f of x equal to negative x squared times x squared minus 9. First things first, solve that, equal to 0. I get x equal to 0. Oh, geez, that's the wrong tool. That one. x equal to 0, x equal to plus or minus 3, I have intercepts. So straight away, I could put x equal to 0, I'll go plus 3, sorry, plus 3, minus 3, yeah? Let's find my first derivative, f dash of x equals 4x cubed. Solve that equal to 0, I get x equal to 0, x equals plus or minus 3 on root 2, which are stationary points. So stationary point at x equal to 0 and at 3 on root 2, what's 3 on root 2 roughly equal to? 3 over 1 point, what is root 2? 1.4. So 3 over 3.5, what's that? 3 over 3 on 2, which is close to 2. Probably not, but that's okay. No, 1.14 is not 1.5. Oh, what's 1.14? So it's 3 over 11 on 10. What's that? 30 on 11. So it's closer to 3, isn't it? Anyway, so we have stationary points. We'll say in there somewhere. Second derivative equal to 0 at plus or minus 3 over 2 root 2. So what's that? Square root of 2, 1.1, 1.1. So it's about 3 on 2, about 1.5. So we'll call it there. So they're my points of inflection and all, okay. Okay, so what does it mean? Let's go through everything now. All right, so straight away we know that there's no points of inflection because my first derivative and second derivative don't both equal 0 at the same point. So I guess from my, without necessarily knowing what the shape of the graph is, let's see if we can work out a few things. So at x equal to 0, I have a turning point. At x equal to 0, f dash of x is also equal to 0. So that makes, the intercept at x equal to 0, stationary point at x equal to 0 as well. If I put x equal to 0 into the second derivative, I get 18, which is positive, which means at x equal to 0, I have a minimum. Something like that. Excuse me. X equal to plus or minus 3 are just intercepts. All right. Okay, so what about if I put x equal to positive 3? If I put x equal to positive 3, I get negative 12 times 9, sorry, wrong one. I get 27 times negative 4 plus 18, so I get a negative gradient. So I do know that x equal to positive 3, I've got a negative gradient. At x equal to negative 3 cubed is negative 27 times negative 4 is positive. Positive 100 and something minus 54 is a positive gradient. So I know at negative 3, I've got a positive gradient. I do know that I have stationary points at 3 on root 2. If I put 3 on root 2 into my derivative, my second derivative, I get negative 12 times 3 on root 2 squared, which is negative 12 times 9 on 2, which is 108 on 2, negative 54. Hopefully we can quickly see that they're both going to be less than 0, which means they're both maximums at that point. So up here, I've got maximums. So very quickly, hopefully we can see that our graph comes to our maximum, into our minimum, up to our maximum, down through our intercept. Yeah, so it ties in with all of the different things that we've just had there. So again, if we grab my, just move that out the way a little bit, we can see the actual function. And again, all the points tie off, don't they? So I'll let you analyse the graph a little bit. I guess the newest ones for us now, second derivative there and there equal to 0 correspond to points of greatest gradient. Yeah, so that's where the gradient is its steepest on the original function. So they're my points of inflection as opposed to stationary points of inflection. What else does our little notes have to say for us? There is no common point where first and second derivative equals 0, so it's safe to assume there is no stationary point of inflection. Points of inflection are where the gradient is at its maximum or minimum, therefore the point where the curve is at its steepest, those points I've just highlighted, are 3 on root 6 or negative 3 on root 6, which is our, what have we said, 3 on root 2 point. Okay, I did mention, I'll leave that out the way, concavity. So we talk about concave up and concave down. And so something that is concave down that way, concave up that way. All right, so if f dash of x is greater than 0, all right, that means the curve, the gradient of the curve is increasing over that interval, all right, which means our graph will be concave up. So it's saying the tangent will lie below the curve. So there's my tangent line. Whereas tangent lines for a concave down, the gradient is above the curve. All right. If we have a point of inflection, oh, that's a bad point of inflection. The tangent line swaps below or above. So, sorry, let's do a different point of inflection. So there's my point of inflection there. So I've got tangent line above the curve, and then all of a sudden, the tangent line becomes below the curve. Because if I do a tangent line above it, I'm going to cross the curve, aren't I? That's why we can't have it there. So a point where the curve changes from concave up to concave down, or from concave down to concave up, is called a point of inflection. So concave down, concave up, my point of inflection. I think a nice thing to really pay attention to with talking of all these points of inflection and things like that is a point of inflection occurs where the sign of the second derivative changes. Yeah, so the sign, so we go from here, the second derivative, it's concave down, so the second derivative is positive. Second derivative is positive there, it's 0 at that point of inflection, and then the second derivative becomes positive, concave up, it becomes positive here. All right. So I think that's really important. So then what this last part tells us, if there's a point of inflection, so if we know there's a point of inflection, by definition, assuming both derivatives are defined, at x equal to a, f double dash of a is equal to 0. Okay? But what we're saying now is that when it says the converse, just because the second derivative is equal to 0, okay, it doesn't make it a point of inflection because it could be a stationary point. Well, it doesn't even. If we think of the x to the 4, if y equals x to the 4, I get 4x cubed and 2x squared. So at x equal to 0, f double dashed of x of 0 is equal to 0, yeah? But clearly, the graph of x to the 4, yeah, so f double dashed of 0 is 0. So at 4x to the 4, my second derivative is 0, but clearly it's not a point of inflection. So I've got a funny feeling I misspoke fraction earlier. I think the key thing, if we're told there's a point of inflection, well then we know the second derivative changes sign. That's what we need to check for, okay? So just because the second derivative is equal to 0, and I reckon I sort of said that in some of the earlier graphs, just because the second derivative is equal to 0, it doesn't necessarily mean there's a point of inflection. We have to make sure that to the left and right of that point, the second derivative is changing sign. It's positive or negative, either side of that point that we're interested in. Okay? Righto. Our second derivatives, just make sure. So in terms of just finding anything there, for each of the following functions, find the coordinates of the points of inflection of the curve and state the intervals where the curve is concave up. So let's work with that one. F of x equals x cubed, f dash of x is 3x squared, f double dash is equal to 6x. So clearly at x equal to 0, f double dash of x is 0. Just as clearly, to the left of that, I'm going to have a negative gradient. To the right of that, I'm going to have a positive gradient. Therefore, it definitely is a point of inflection. All right. So f dashed is equal to 0, and the curve changes concavity. So f double dashed is to the left negative, to the right positive. It's a stationary point of inflection. All right. And for the second part, it's concave up, where the second derivative is positive, so from 0 to infinity. Similar, if f of x equals negative x cubed, well then my first derivative is 3x squared, second derivative negative 6s. Again, f double dashed equal to 0 means that x is equal to 0. Yeah, probably so. I don't probably like the way this is written now, therefore the point of inflection. So I reckon I'm going to change that. So, really what we're saying is that since f dashed of 0 is equal to 0 and there's a concavity change, it's a stationary point of inflection. All right? Let's just check our justification in the others. All right, f of x equals x cubed minus 3x squared plus 1. F dashed of x, 3x squared minus 6x. F double dashed of x is 6x minus 6. So at x equal to 1, f double dashed of 1 is equal to 0. So, again, I think it's probably the nature of the second derivative. You can infer almost straight away that if I pick a value slightly bigger than 1, say 2, f double dashed of x is positive. If I pick a value less than 1, say 0, f double dashed of x is negative. So there's a change. Okay? So because there's a change, there's a point of inflection, but because f dashed of 1 is not equal to 0, it's just a normal point of inflection. All right? And we've got a concave up between 1 to infinity. All right? I guess that's the other giveaway too. If your function's concave up over the whole graph or concave down, well, you know that there's no points of inflection. Okay, so what have we got here? The math's probably a little bit messier. F of x equals 1 on x squared, so quotient rule. Okay, derivative of the bottom is 2x, so derivative of the top is 0 minus derivative of the bottom. So there's my negative 2x over. Now if I differentiate that, just take your time deriving. I'm not going to go through the whole process. Step it out. So derivative of the top is negative 2 times the bottom minus derivative of the bottom, which has got a little bit of chain rule in there, times the top, which is the negative 2x at the back, will give me x squared minus 4 over x squared minus 4 to the 4, and that term there in the bracket. My x squared minus 4's can cancel to make it an x squared minus 4 to the 3, and I get 6x squared plus 8. So what does that tell me? That can only be, well, first things first, x squared minus 4 can never be 0, because that's the denominator. And 6x squared plus 8 will never be 0 because x squared is always positive and we're going to add 8 to it. So at no point is their second derivative 0. So there's not going to be any points of inflection. All right. If we want to talk about concave up, we want to have the second derivative positive. All right. So since x squared is always positive. Okay, think about the change of sign. Well, actually go the other way. 6x squared plus 8, the numerator is always positive, so we can only be negative if the denominator is negative. So if the denominator, for the denominator to be negative, I need the magnitude of x to be less than 4. In other words, x has to be in between negative 2 and 2. So there's my concave down part of the graph, yeah, which means it's concave up everywhere else. And we know from our asymptote knowledge that x equal to plus or minus 2 is a asymptote. And so there's our concave up graph. But note there's no points of inflection. All right, so hopefully we're getting a little bit of a feel there. Long sort of exercise, this one. Let me just... Oh, it's there anyway, so it doesn't matter. We'll check it later. All right, sketch the graph of the function showing all key features. All right, so the fact that I've got the answer there down low, that doesn't matter. Let's just slide that across there somewhere for now. All right, so what have we got? Let's work out f dash of x. So I've worked out the first derivative, which gives me negative 6 on x squared plus 3 on x. If I take a 3 on x out the front, I get 1 minus 2x. So when's that going to equal 0? The only place that will equal 0 is at x equal to 2. So I've got a stationary point at x equal to 2. Let's work out second derivative. F double dash of x gives me that. Where have I put x equal to 2 into that? No, don't know if I have. If I put x equal to 2 into my second derivative, I get 4 over 2, which is 2 minus 1, which is positive 1. 3 over 4, so I get a small positive value. So in other words, it's the second derivative, well, there it is there, f double dash of 2 is greater than 0, so the graph is concave up, so it's a minimum at that point, okay? If I put x equal to 2 into the function, I get 6 on x, which is 3, minus 6, which is negative 3, plus 3 natural log of 2. Now log base c is log 2.7 to the 2, the number is 2, which makes that a very small positive number. So I get negative 3 minus a number close to 1, so I'm going to get a small negative number. So that point there is going to be at 2, something small and negative. All right. What about the concavity of the graph? As I've said, 3 on x squared is positive everywhere. So where are we going to have it equal to 0? Just when x is equal to 4. So that's a point of inflection. All right. So I've already decided that at x equal to 2, the graph is concave up. So it's going to be concave up. The only place it's going to change concavity is at x equal to 4, about here. Yeah. Otherwise, it's concave up everywhere. All right. Solve the... what do I want to do? I find my x-intercept somewhere. I don't know if I did I? Maybe we just looked at maybe I just guessed it a little bit. Well, clearly we can see if I put x equal to 1 on reflection, 6 over 1 is 6 minus 6, which is 0. The natural log of 1 is also 0. So, well, there we go. At x equal to 1, I'm not even looking properly. F of 1 is equal to that, so I get the 0.10. So there's my intercept. I know the graph is concave up all the way through until I get to the point x equal to 4. So I'm going to draw a concave up graph all the way through till I get to my turning point until I get to x equal to 4. Then I know it changes to be concave down. Okay, so there is obviously another x-intercept in there somewhere. Let's consider the nature of the graph. If I consider as x approaches infinity, what happens as x approaches infinity? I get 6 over a big number, which is basically 0. I've got negative 6 plus 3, what happens to the log graph as x steadily increases? Well, it gets bigger and bigger. So I end up with -6 plus a biggish number. So my graph's going to steadily increase. And I know it's also going to do that because it's concave down the whole way, but it's an increasing function. Right, so now if I drag my original or my calculator template in, you can sort of see that it's not bad. Key features, concave up all the way through until we get to x equal to 1, 2, 3, 4. At that point there, our concavity changes. And it's really hard to tell, but you can see that the graph's just got that little bit of a curve to it. Yeah. That's about it, I reckon, showing all key features. So would you be asked to, well, you wouldn't be asked to solve for x-intercepts. Showing the key features really is about just labelling where maximum or minimum may occur, where points of inflection occur. I guess that's the key change, if you like. So let's just formalise some of the terms and things that we've been talking about now. So my second derivative, what does it mean? So I think let's just start with first derivative. First derivative is 0, second derivative is 0, stationary points of inflection. Okay, assuming there's a sign change. So what have we got if the second derivative is 0? If second derivative is 0 and the first derivative is positive, we'll have a point of inflection and there's a concave up. Yeah, so the curve is concave up at that point. If the second derivative is below 0, it'll be concave down. So we've got that concave down nature. If the first derivative, if the second derivative never equals 0, that means it's always going to be concave up or concave down. Okay, so if my second derivative is less than 0 the whole way, it's concave down the whole way. There's no sign change. All right, and similar for the positive. All right, so I guess in methods we sort of came across a sign diagram, so it's perfectly acceptable in methods for you to determine a maximum or minimum by using the second derivative test. All right. Must be pretty close. How many questions? All right, we'll keep moving. Just slide that across. Consider the function of the rule g of x or e of x, find g dash, find g double dash, and on the graph sketch everything. Okay, so I guess for all intents and purposes I've done that, haven't I? G dash of x is just 2xe to the x squared. Let's get the yellow pen. G double dash of x gives me a 4x squared plus 2e to the x squared. So we've done that. On the one set of axes, sketch the graphs. So let's think about e to the x squared first. We know the e to the x graph, and if x is greater than 0, e to the x just looks like that, isn't it? Well, e to the x squared, if x is greater than 0, is just going to be sharper because the x squared values are going to get bigger more quickly than e to the x. And then if it's e to the x squared, the negative values are just going to be a mirror image of the positive values, which is where we get that, the red line there on e to the x squared. X equal to 0, e to the 0 is 1. If we consider what happens in purple, let's sneak down to the g double dash of x. We get 4x squared plus 2e to the x squared. So what's 4x squared plus 2 going to do? Well, that's just positive numbers already, times. So really I've just got this positive number at the front of e to the x squared. And what's that going to do? Well, it's just going to be a dilation factor of really by whatever that positive number is, steadily increasing from the x-axis. So again, if we put x equal to 0, we get e to the 0, which is 1. and we get 2 in purple, so we got that point there at 2, oh, that point there at 2, 0, and then the graph is steadily increasing. Come back to g dash of x, I've got e to the x squared, which is positive the whole way, we've just decided that, multiplied by 2x, which obviously means if x is equal to 0, the function will be 0, and then we've just got an e to the x squared steadily increasing. If x is less than 0, 2x will be less than 0, so we're going to have negative values coming back down through that way. All right. So there's our graphs, and I might bring our graphs across just to show that that's roughly what we've got. Solve the equation g dash of x equal to 0. So we've got the green function there, 2x e to the x squared. We know e to the x squared will never be 0, so it's only ever going to be at x equal to 0. Oh. So we've got that there. Show that g double dash of x is greater than or equal to 0 for all of x. So formalise that. Oh, that's this part down here. So we spoke about that. So just formalising, I guess. E to the x squared is greater than or equal to 1. We know that. Okay, for all x, since x squared is greater than or equal to 0 and e to the 0 is 1. All right, so we've established that e to the x squared is 1 or more. 4x squared plus 2 is greater than or equal to 2 for all x, for obvious reasons. Therefore, the whole function is going to be greater than or equal to 2 in actual fact. So we've shown what we need to. State the intervals for which g dash of x is greater than 0 and g dash of x is less than 0. So g dash of x, we decided at x equal to 0, we know that e to the x squared is positive. So the sign change is only going to occur when 2x causes a change in sign, which is obviously going to be at x equal to 0. All right, but you just formalise, just state those things though. All right. Where we go? We got left. Just about done. Oh, that must be. That's where it is there. Okay. X squared 10 minus x. So we've got a cubic. So we're dealing with a function that we're very familiar with, but we can use our second derivative information just to confirm some details. Okay, find the coordinates of the stationary points and determine their nature using second derivative. All right, stationary points, f dash of x is equal to 0, x equals 0, we get x equal to 0, x equals 20 on 3. So, find the coordinates. So, again, probably substitute x equal to 20 on 3 into the function, and we get, as it turns out, 148.15. What sort of stationary points are they? Well, at x equal to 0, 0, at x equal to 0, f double dashed of x is positive, which makes 0, 0, which makes it concave up, which makes it a minimum. At x equal to 20 on 3, f double dash of x is less than 0, which makes it concave down, which makes it a maximum. So there's the nature of my stationary points. Find the coordinates of points of inflection. So I need the second derivative equal to 0. So hopefully I've done that somewhere. F double dash of x is equal to 0. We get x is equal to 10 on 3. X is equal to 10 on 3. Find the points of inflection, find the gradient at this point. And at 10 on 3, my gradient is 100 on 3. So I guess graphically, on the one set of x, sketch the graphs over 0 to 10. So if we look at our graph here that we've got, I'll just use the one I drew. We can sort of see it all ties in. So we're sort of saying that I've got my maximum where the first derivative is equal to 0. I've got what turns out to be a point of inflection where the first derivative is equal to 0. At 10 on 3, which is there on the purple line. Okay, I have a sign change on my second derivative. My second derivative goes from being above the axis, which is positive, to below the axis, which is negative. So at 10 on 3, that corresponds to a point of inflection on the original graph. And the gradient of that line on that graph is 100 on 3, which ties in because it's a positive gradient at that point, isn't it? Okay. Finally, undo that, keep them all together. Use a CAS calculator, that's better. Now we're allowed to use the calculator. So let's slide that across again now. Use a CAS calculator to find the stationary points and points of inflection of the graph. So really, it's just keeping track of everything on your CAS, yeah? So the function was e to the x sine x, so what have we done? Derivative of e to the x sine x, oh, we don't want to use that one first because I didn't have the, obviously my calculator was in degrees, not radians. Derivative of e to the x sine x is e to the x cos x plus e to the x sine x. Solve that function equal to 0. I get x equal to 3 pi on 4 or 7 pi on 4. Substitute those values in. There's my stationary points. All right. Points of inflection means the second derivative, or the first derivative, which is e to the x cos x plus e to the x sine x. I differentiate that. I get that 2e to the x cos x. Solve that equal to 0 between 0 and 2 pi. I get pi on 2 and 3 pi on 2. So they're my points of inflection. And that's all I have to know. Just tie that in with the graph, I guess. Yes. There's my original. So what have I got? I've got, oh, a bit hard to read. Turning point at 3 pi on 2. Another turning point at 7 pi on 4, which is what we said sort of back there. We can work out the values. Points of inflection, where my second derivative equals 0. So that corresponds to about there. Gradient changes from being its most steep to flattening out again through there. All right. So look, it all ties in. Hopefully it makes some sense. It is a long sort of exercise, but yeah, maybe stop and rehash a couple of these things and go through a few of these things again just to consolidate. Righto.